I'm Jung Sabam, who is in charge of presenting the group project for the computer security. We conduct research on the subject of Einstein, a data-only attack automation tool. The table of contents is as follows. First, team introduction. Second, paper research. Third, implementation. Last, conclusion. First of all, here's an introduction to our team. No Kyung-bin is the team leader and is in charge of implementation and making PPT slides. Park So-jun is in charge of paper research and making PPT slides. And I am in charge of paper research and this presentation. A data-only attack is an attack technique that manipulates program data without altering the control flow. Because the execution path remains legitimate, these attackers can easily bypass defenses designed for traditional control flow hijacking, such as DP, AS error, and even modern CFI. In other words, even if the control flow is fully protected, the data that feeds into system calls may still be vulnerable. This makes data-only attacks an increasingly attractive and practical approach for attackers. This paper focuses on making data-only attacks practical and automatically generatable. Traditional DOA research relies heavily on symbolic execution, which suffers from state explosion and low scalability. The key contribution of the paper is Einstein, a lightweight exploitation framework that uses dynamic taint analysis instead of symbolic reasoning. Einstein also identifies attacker-controlled data flows targeting system calls, generates exploit payloads, and verifies them automatically. The result is a fast, scalable, and highly practical method for producing real working DOA exploits. First, dynamic taint analysis replaces symbolic execution. Einstein avoids complex constraint solving by tracking only concrete data through real execution paths using dynamic taint analysis. Second, attackers don't need Turing-complete gadgets. In practice, attackers only need to control syscall arguments, such as those from execve, write, or send, rather than assembling full Turing-complete gadget chains. Third, programs already cause useful syscalls. Because programs naturally invoke these syscalls during normal execution, the attacker does not need to modify control flow, meaning CFI is bypassed by design. Four, identity data flow is common. Many security-relevant values propagate unchanged through the program. Einstein leverages this identity data flow to reliably connect attacker-controlled inputs to vulnerable syscalls. This is our Einstein pipeline. First, taint attacker writable memory. This models an arbitrary write primitive by tainting all attacker writable memory regions. Second, monitor security-sensitive syscalls. During executions, it monitors sensitive syscalls such as execve, write, send, to check whether any of their arguments become tainted. Third, detect identity data flow. If a syscall argument receives an attacker-controlled data through an identity flow, meaning the value is propagated unchanged, Einstein flags it as a potential exploit point. 4. Generate candidate exploits. Based on this analysis, the framework automatically constructs override payloads that can influence the syscall. 5. Re-execute and validate Finally, Einstein reruns the target program and verifies whether the exploit actually works in a real execution environment. Using this pipeline, Einstein analyzes NGINX and automatically identifies vulnerable syscall chains. It searches for usable gadgets, examines how NGINX handles and propagates data, and determines where attacker influence is possible. After generating an attacker payload, the system verifies the exploit through actual program execution, ensuring its effectiveness. This entire process requires no manual gadget chaining and no symbolic reasoning. I'll briefly introduce the process of the practice and demonstrate the actual attack situation using Einstein. We explored vulnerable system calls during the practice and gadgets that could be used for attackers. And we tested NGINX, the target app, to see the normal behavior patterns and to see how the manipulated data works in the app. After that, we developed an attack scenario and wrote a payload accordingly, used it to generate an attack and checked that it worked as intended. This is the result of using Einstein to find vulnerable system calls. You can see that NGINX alone has found over 1,600 gadgets. And based on the previous results, we created the exploit through Einstein. You can see that there are quite a lot of actual working exploits. Among them, we conducted additional verification using code execution exploit. We assume that a memory overwrite vulnerability exists in NGINX, the target program, and created a situation in which an attacker performs memory overwrite and then attacks NGINX's worker process to execute the desired code through the execute function. Here is our demo. We run the NGINX program first. Since we assumed that there was a memory overwrite vulnerability, we arbitrarily modified some values. After that, if I kill the worker process, you can see that the file hack was created, which can confirm that the attack was successful. The emergence of data-only attack and Einstein calls for significant changes to the existing cybersecurity paradigm. As traditional control flow defenses are disabled, the need for new detection and defense strategies is increasing. Data-only attack can also pose a wide range of security threats across the software supply chain and server applications. Security personnel and developers should consider data-only attack to re-evaluate existing attack vectors and defense points. Einstein has made great strides in data-only attack automation, but it also has some limitations. First, it is about the extent of the attack. It mainly focuses on system call manipulation, so it may not cover all kinds of complex data manipulation vulnerabilities. In addition, because the generation and destruction cycles of data are not fully considered, there is a limit to automating sophisticated attack scenarios that reflect the time-varying data characteristics. Nonetheless, having hands-on experience with tools like Einstein is essential to deeply understand how data-only attack works and develop response strategies. Going forward, the security ecosystem will require new defense innovations that take data-only attack into account. Thank you for listening.